Can we go over 51 from 3.5?
Bet. You bet, Blair.
Thanks.
So I'll hold off on this thing. And the reason I dragged this thing in today, so if anybody wants to know, so when it comes to, if you don't want to use quadratic formula, you want to use your graph or solver, graphing calculator to solve, a quadratic equation, that's why I brought this in. I know I talked you through last time, but I was looking around there, some people didn't have their PI, you see it up here, it helps the memory to kind of go. And you remember, 3.551. Inverse sine 2x plus 1? Oh, that's a great one. All right. So before this, perfect to give them. Inverse trig derivative. Y equals inverse sine 2x plus 1. Find dy dx. Inverse trig. Okay, we need chain rule, don't we? There's the g. What's the derivative of g?
2.
So let's put a 2 in the numerator. Cool? All right, 2 in the numerator. And we can do this from memory clarity. This is the one with the radical, right?
Right.
Got a radical. The cosine does the negative. This is the positive. And we write in the radical 1 minus whatever this thing was squared.
The book had something different. I think that's why I was confused. Because
So Claire did it right.
I wrote that, but the book had something really weird.
Claire got it right. She's saying, she goes, but the book did something weird in the back. We're gonna figure out how they wrote it that way. First of all, pretty good, huh? That's it, there it is. There's derivative. 2 over 1 minus 2x1. Now, if this was just 2x, I know you could get in your head, everyone. What's 2x squared? It'd be what, 4x squared? But the book did something different. So I imagine they expanded this. Let's start with that. All right, so we'll just keep doing an equal sign. How did the book write this in? All right, let's FOIL that 2x plus 1. All right, what do we get? 1 minus, let's keep a parentheses around that. 4x squared plus 4x plus 1. All under the radical, but I haven't distributed the minus yet. So far, so good? Cool. I'll swing it back over here. Now I'll distribute that minus. All right, minus 4x squared minus 4x minus 1. Any like terms in there? What do you think, Claire? Any like terms?
1.
I'll flatten this. Oh, the 1 minus 1. So now we're going to see why the back of the book was able to do just a tad. Because this one and that one, what?
0.
Vanished. So you got a negative 4x squared minus 4x. So far, so good. Well, Claire, can we factor a number out of the 4s? A 4. Isn't 4 a perfect square?
Oh, that, and then they
Yep.
canceled out the 2 and the
Yep.
4. Oh, okay.
So when I'm going to show the factor and they're like, oh, we got to factor out a 4 out of that. You get negative x squared minus x. Some of you are like, factor out the x. You can if you want. But it's really that 4 they're dealing with. It's really the 4. And then the square root of 4 is what? 2. 2 divided 2 is, so you can write this final answer as 1 over square root negative x squared minus x.
Would you take off points if we wrote, like if we didn't
Like that?
oil it?
I'm fine with that.
Okay,
I really am. I think it's good to do this though.
yeah.
You go, why? In case, you know, this was helpful to you some ways. You're like, well, if I do this, it helps me do a problem later on in calculus a little bit easier. That's totally fine.
Okay. Can you do 62 as well?
You bet. 62, same section, right? All right. I like this. Arctan x squared minus x. Find the derivative. All right. Arctan. I love arctan because there's no radical. Carries.
Mm-hmm.
Cool. But hey, Claire, you're good to go there, right?
Yeah,
Good.
the only thing I was worried about is I thought I did something, like I understood something incorrectly because I didn't get the answer that they had, but I wasn't sure if they like simplified it to something weird. They did.
And I know you know how to do this. I know you know how to do this.
Yeah.
But it was there that they decided what?
Yeah, I was like.
That's a neat trick. You might find that very, what, the idea of taking out a 4, you might find yourself doing that more often, like in maybe Calc 2.
Okay.
You might. A couple problems. I'm trying to think in Calc 2 where it's like, yeah, you can just factor out the 4, put a 2 there. Count raise. All right, here another one. 56. Find dy, is that right?
62.
Oh, way off. 62. F of x equals arctan x squared minus. Find derivative. All right, there's your g. There's your g. What's derivative of that?
2x minus 1.
2x minus 1. I'll put that up there. Chain rule. 2x minus 1. How do you call arctan's derivative?
1 plus
1
x,
over 1 plus.
x squared.
Yeah. And so in this case, 1 over like 1 plus g squared, where that's my g. This over 1 plus all that. This one or this one? There's your g. Or your u. All this. Then what?
Square.
And we're done. But then, Kel, is that the answer in the back of the book?
No.
So they did something with the bottom, right? All right, let's play with this. Let's expand that. All right, I want, what's an x squared minus x? X squared minus x.
X to the power 4 minus 2x cubed plus x squared.
All right. All right, I'm gonna do that. 1 plus x to the 4th minus 2x cubed, we're foiling, plus x squared, right?
Mm-hmm.
And we get 2x minus 1 all over x to a 4th minus 2x cubed plus x squared plus 1. And you can look at that and wonder, can you factor anything out of the bottom? No. How'd the back book write it?
They're not in, that, the evens aren't that good.
Oh, they
I'll
didn't
let you know
have
if I
these.
did it right.
Yeah, oh yeah. This is fine. This is fine, I did want you to look at it, Cal. You might say, well, maybe I can factor this by grouping and then cancel this. But you could check it out, when if you factor by grouping won't work, because you factor out x cubed, you'll be left with an x minus 2, and that doesn't match this. So I didn't want you to think you can factor by cubing. It's fine. Differentiate it correctly, good job. And probably the funniest thing, everyone, most of the time in Calc 1, even Calc 2, you're just dealing with this guy. Just this lonely arctan x. And that derivative is just 1 over 1 plus x squared. Seriously. And then later on, I don't know, after July 4th, you and I will do the antiderivatives. And out of the blue, this will pop up. You've learned all these techniques, and that thing will just pop up in the middle of all these problems. And you go, wait a minute, and you go, oh yeah, that's the arctan. And you'll say this equals arctan x. The idea of going backwards. We always put a plus a constant there when we do it. And even, this is another thing, what if this had a 5? All you do is you put the 5 out here, and you put an answer like that, because of the constant rule. Constant rule applies with the antiderivatives as well. So that's really what's going on, so you can see that. It's a great one. Any others?
I had a question. It's not from the textbook, it's from a review book.
Yeah.
The problem was find the derivative of natural log of e to the x over e to the x minus 1.
All right, natural log of e to the x over e to the x minus 1, and it said find the derivative, right?
Yeah.
All right, let's do it. First of all, I'm looking at that thing. Do you know any log properties?
Yeah.
There's 3 ln properties. One of them is where you can move that power in front. And before I work that problem, you might find that helpful. So let's just review, pre-calc log properties. There's only 3. The first one is ln a over b. I can write that as natural log of a.
Minus-
Someone in here knows.
Minus ln.
Minus ln b. So you might find that property helpful in that problem. You might be looking at it now going, oh, I know how to do it now. So that's one thing. Might as well do all the other ones. Does anyone know what a times b is?
A plus
ln a
plus b.
plus ln b. The third property, everyone, of logs, if you got like an a to a c power,
C
you can
co-
scoot that c where?
Front.
You can scoot it in the front. So these are just log properties. So you can write that as c natural log of a. But there's only 3. I don't think there's like 100. It's only three log properties. There you go. Some call that the quotient rule. I don't like that because there's a quotient rule for derivatives. So I don't want you to confuse yourself. Some call that the product rule for logs. But I don't want to confuse you because it's a product rule for derivatives. There you are. Hey, so I'm going to try that. I'm going to start this problem with what? ln of x minus ln of EDX minus 1. And I'm going to find this thing eventually. So I like your problem you got from the review book. Before we even go here, we can really like this neatly
1.
by these properties. So let's go over here. Can I move that power?
Mhm.
EDX now? Everyone's like, yep. Move that x to the front of ln of e. Before I do the derivative, what's the natural log of e?
1.
So let me get this, before I even start, it's like, that's just x. Natural log of e is 1. The natural log of e to the x, just x. So now I'm going to do it, everyone. Wow. Now let's differentiate y with respect to x. That's a simple what? Oh, that's a 1. But now, do you remember how to do these? We put this in the what? The denominator?
Mm-hmm.
And then chain rule, what's the derivative of e to the x minus 1?
E to the power x.
That'd be e to the x plus a 0, right? Is everyone okay with that? Remember how you do natural log derivatives? Factors there, then I multiply the derivatives, put it here. So this is the answer, but I imagine in that workbook, they got it in one fraction. So let's do common denominators, everyone. What would I have to multiply here?
E to the power x minus 1.
E to an x minus 1 all over
e to the x minus 1. It looks like I get e to the x minus 1 minus e to the x all over e to an x minus 1. And sure enough, what cancels in the tops there? They subtract out, right, Claire? They're like e to the x minus e gone. So the final answer should see this in your workbook. I like your problem. That should be the derivative. There's nothing else we can do. Like we can't, no, that's it. That's the prettiest we can make it. Good job. I mean, there's other ways to do it. I just thought that was easier. Deal with the properties first. Get it clean. We got it here, and then you're like, okay. Okay, I'll work with that now. A good one. Very good. Any others? I'm looking at Amber. She got it from a workbook. It was a neat problem though, but these were helpful at the beginning. And then when we got to here, we were like, wait a minute. You can kind of move that X there. And that was just, before we even differentiated, we did 3 like rules of pre-calc before we even got started.
Oh, the ln and the e cancels out, so it was just y equals x
Yep.
minus.
But then here, when we got to here, we're like, all right, now it's time to differentiate. That's a nice 1. And then this was the e dx minus 1 on the bottom, e dx. ln derivatives are great, aren't they? All right. Hey everyone, today, before we get into related rates, I still want to wrap up 3.7 and talk about that calculator tool. A lot of you are nifty with it, which is great. It's just sometimes you can avoid the old quadratic what? Formula. When you got to solve some quadratic equation, you're just like, I'm going to write it as a decimal anyway when I use this tool. Key word is facilitate. It facilitates it. So I'll go back to that same problem you had before. It was in 3.7. It was number 9, right? That's the first part. We breezed through that. It was that second part. When they said, what is the velocity of the rock when it was 25 meters its height. I'll write that.
Is this section 3.7?
When its height was 25 meters. Remember when someone threw a rock and it went like this? So 25 meters, how many times did it hit 25 meters?
Twice.
Twice. So the question asks, what is the velocity of the rock when its height was 25 meters? And they start out by going, on its way up. So there should be 2 answers to that quadratic. All right, what was the height equation? H equal? Let me look.
15t minus 1.86 t squared.
Thank you.
No problem.
All right. So first the setup. When we started this problem, the first thing we did was, we set 25 for height, right?
Mhm.
It's this. Right here. Quadratic form. We'll set it all equal to 0, right? Remember, I'm gonna add this on both sides. I'll subtract this on both sides. I get 1.86 t squared minus 15t plus 25 equals what?
0.
0. Now I'll go to this calculator here. Unless you want to do quadratic formula, which you can.
Actually, in my Casio, you can do it too.
Hey, cool! There's scientific Casios, everyone. The scientific Casios are pretty cool. And they're cheap too, aren't they?
Yeah, oh, like $17.
Yeah, $17. That's some really neat stuff. All right, let's build that. I'm gonna use this thing. So clear, let's go up here. I go to y equals, and what do I type in? I didn't want to use t, so I used x. 1.86 x squared minus 15x plus 25. Now, one way I can do this, I can hit the graph, I can use the intersect button, hit enter, 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 and it'll give you my answer. Isn't that cool? That's how fast it'll be. The only thing is, be careful of this. If you want to do this like on Tuesday's test, make a note. If you're going to use the intersect button, guess how many equations you got to have written here? 2. So if you only have one, calculate intersect what? Right? And it won't work. So I need another one. So what is that equation equal to? Go to 0. By the way, you could have done these 2 equations. Do you agree? But I always like to make it all equal to 0. So let's go down here and say, all right, equals 0. So this is one technique. Now I hit graph. If my window's out of whack, I hit zoom 6. I hit trace. And I like to get the cursor. Where is it? Follow those numbers. I'll make it zoom in so it's a little bit better looking. There you go. That's a lot better. I want to get my cursor close to it. That's close enough. That way the calculator will run to that 0 right there. Claire,
Wait, is it minus 25 or is it plus 25?
you're the best, is it?
I think it's.
Let's see, is it?
Plus.
I think it's close.
What I did was, Claire, I added this to both sides,
Okay,
then I subtracted this.
okay.
And Claire, something else you could have done, I'll be honest. You know how I set this equal to 0 like this? You could have set that as one equation, and that as another one. And it would have done a straight line, but then you'd have to play with the window. Because at y equals 25 is really high up.
Right.
I just like to get it all equal to 0 so my eyes can focus on the x-axis, right?
Yes.
And so I do this, and I hit trace, Claire, and I get it close to the answer. Oh, that's close enough. Now I go to second trace, which is calc. Which one's intersect? 5, hit 5, and I just hit enter, enter, enter. I might have to look. Enter, enter, enter. What's the answer? 2.35, 24952. All right, done. There it is. Now, is that the time when it was on the way up?
Down.
2.35, 34952. Don't focus on the shape of this graph. But Evan, isn't there another answer? Isn't it at a later time? So remember, someone threw the rock like this. It went up and then it went down. So wouldn't that have to be the time on the way up? Now, if you want to do the one on the time coming down, wouldn't that be the later one? Does that make sense? Cool, great.
If you got like 2.34, that wouldn't make a big difference, would it?
It would. It's going to throw your final answer off a tad. You'll be close to the answer. So that's why you want to use intersect. So you get it accurate to what? All these places. Now here's the great news, when I did all this, maybe you're sitting there going, oh man, I gotta copy this number down, write it down. No. Well-designed calculator here. I'm gonna hit quit, okay? I'm just gonna hit X on my calculator. Guess what it's gonna tell me X is? Isn't that cool? Very well-designed calculator. So it knows when I do that, it's gonna store that number into what letter? X, so then you don't have to worry about what? Copying it down, stuff like that, so it's there. I think I'm done this problem except for one thing. What did they ask? Let's go back. What is the what?
Velocity.
So where do I have to plug this?
At the derivative.
Oh, what was velocity again?
15 minus 3.72 t. How much? 3.72, I guess. 1.86 times 2. How much is it?
Am I right? And then I substitute what? I'm gonna stretch it out though, I don't wanna round it.
Oh, you have
The
to
rule of
put,
math, I don't round to the final answer. 2.35, 34952. And I plug it in here, so look what I'll do. Watch how I type this on my calculator one. 15 minus 3.72, watch what I do, times what letter?
x.
It'll do that for me. Cool, because X is that number. I made sure it was that number. There it is. So the calculator is designed to facilitate this kind of stuff. If you know what, I spent 10 minutes, quadratic formula. Write out all these places, right? And all this stuff. It's there for you. Now, is there a solver on this calculator? There is, I never use it. I solve everything with the graphing tool, because you get to see all the solutions. What if a graph hit the x-axis five times, there's 5 answers? Or 2 times, or 1, what if the graph never hits the x-axis? There's no solution, right? So that's why I think it's a great way to approach it. Couple other things to talk about. What if I didn't put that 0? Is there another way to do this? Yep, go up to that menu. What's number 2 say? 0. So if you do this, the only reason I didn't do this first, you gotta hit more buttons, watch. 0, that's an x-intercept. So if I hit this, first of all, I'm gonna make sure my trace is near there, my cursor. So I'm gonna trace and just get near there again. Come on down. All right, there it is. Close enough, right? All right, second calc, 0. Left bound, you gotta make sure cursor's on the left side of that x-intercept. It is. Hit enter. Right bound, you gotta move the cursor to the other side. Then hit enter. Then guess just hit enter. But you notice I had to hit more buttons, I had to look at it before I could just go like this, right? So I prefer intersect. If you remember, put the equal 0. True? So that's another way to do it. I'm trying to think, anything else? I don't think anybody in here would have to do this, but I might as well show you something. I seriously don't think anybody's ever gonna need this button. You know what Math 8 says?
Derivative.
N deriv. So what if I said n deriv, what was that original function? 15x
Minus 1
minus 1.86 x to the what?
square.
I'm gonna put comma x. I just don't think anybody in here is ever gonna need this, but I'd like to show it to you for one day. You go, oh, I'm gonna use this. I'm gonna ask the calculator to take the derivative of this and then substitute for the x that number. Okay? Right? Comma, here we go. What is it? 2.35, 3495 what? Did I get the same answer? I just don't think you know, wow, whoop-de-doo. Because was it hard to do that derivative? See? Did you like that? That was Math 8. Go to Math 8. See, this is n deriv. Let me look at it. Oh, it's got the update. It's updated. That's fine. Still work. You may prefer it in this mode. Let's see what you got. See it? And you put it all in there, and then here you're gonna have to put the 2.35. But make sure you put what? Put the h equation. So type 15x. I just use that. 15x. Yeah, there you go. 15x. Don't worry, the x only went off. Just gets to the x. We'll just quit. Yeah, put an x. The x. Oh, cool.
And then here.
Minus 1.868 squared. Oh, whoa, whoa, whoa. Get back in there. Can you left arrow up back in with that thing? Oh, good, good, good.
Oh, okay, so.
Minus 1.86
Square.
squared.
Okay. and
Nice.
then Over here.
In that little box, put, I like your mode.
0?
Nope, look at the box, you gotta put it there. The 2 point what?
Oh,
That
X,
whole thing.
X.
It'll let you do it.
Was X.
I don't know if that'll work, but see, that means X was stored as something else. So I'm gonna hit second arrow, just we can go back in here. Right here. Let's put 2.35, this time we'll manage manually, type 34952. Right?
Yeah.
Oh, I know what we're doing wrong. It's not 18.6, it's 1.86. Amber, I'm gonna be honest with you. I don't know if you're gonna ever want to use that button because is it hard for you to take that derivative?
No.
Not at all. That's what I mean. That's the only thing it was helping us out with. You're like, oh, big deal. I know how to differentiate that. But what if it was something crazy, then maybe it would be nice. Does that make sense? But if there's anything this calculator does in terms of calculus, I'll show you. Show you anything this thing will do. Cool? Great. So use that solver whenever you want, especially if there's application problems. I'll put that off to the side. I don't think we're going to need that anymore. But if you do have a question about the calculator, I'll be glad to do it. Did anybody have any other questions from 3.7? Position, velocity, acceleration, right? PVA going down. The hardest part might be just dealing with the technology to help you solve some of that stuff. That's it. So, you ready for related rates? Oh yeah, I got a handout. I I got a handout on it, but let's. You know, look what section it's in. Not 3.8, it's in what?
3.9.
So when you're like, what, Calc 1, they don't do 3.8? No, they could have, and when, you know what the title is? Exponential growth and decay? Our Calc 2 course puts a couple of those problems in there, so they wait till Calc 2 to do it.
Is that the A equals to E0 KT?
That's it. They, for some reason, they wanted to put it in Calc 2 when you learn separable equations, because it flows better. It's not a bad idea.
But that's very interesting though.
It's interesting topics.
Very interesting.
Oh, and if you talk about like,
The-
carbon 14, and how you can date artifacts. Like they dated everyone, you know the Shroud of Turin?
uh-huh.
They dated that by carbon dating, back in 1988, by the way. But all that stuff, carbon dating, things of that sort, he's right. Population growth, it's an interesting section. This is related rates. All right. So you'll come back to that 3.8 in Calc 2, once you learn the separable equations. What's related rates? Well, to understand this, so let me just go back to this thing. So we can make sense of this section, related rates. X squared plus y squared equals 9. Do you remember how I said find dy dx? You remember what we had to do? We had to use a new technique of I almost said integration, of differentiation. It started with the letter I. remember?
Implicit.
Implicit. And look at the denominator, what's that letter?
X.
So what we did was, we said in our first step, we'll differentiate both sides of the equation with respect to what letter?
X.
X. Does anyone see why? You might have been, why am I always differentiating respect to X? Because in the denominator, that's the letter X. Cool? All right, so that's why, we differentiate both sides with respect to X. That became a what?
2X.
Became 0. But when we did this, it was almost like, you're not X. You all agree? So we used chain rule. And you go, how did it work? We put the 2 in front by power rule. We decreased this parentheses y to a first. And then by chain rule, I'll just put this equals 0 over here. Chain rule said always multiply the chain, which was the g prime. So I'm going to say this to myself and I'll write it down. Then I have to here put derivative of that letter with respect to x. Oh, then that would be derivative of that letter with respect to x. But to keep it simple, every time we did implicit, we said just put down a what? D, y, dx. Every time we differentiate y, it makes it easy. True? But that's why. Everyone okay with that? Yeah?
Why did you put the derivative twice? One is y prime, then again.
Oh, that was y to the first.
Okay.
That's really why I don't like to write y prime down.
Okay.
Because sometimes that one's invisible. All right, so glad you brought that up because sometimes that one's invisible and that's what confuses a student. So I recognize that to I'm not seeing it, I'm like, because there's an invisible one there, and they go, oh. So I'll write it, but we know in math, that means what? Derivatives. So every time I do this problem for emphasis, I'll do dy dx, and I won't put that one there.
Okay.
Because that did look like a y prime. Don't care that? Cool, I did that because what if this was y cubed? It would have been what? 3y to the
2.
second, and this would have still been dy dx. Let me just show you that, look. X squared plus y cubed, this would have been 3y squared, that still stays. Because you go, what's the derivative of that letter? Respect to x. Well, with related rates, everything is with respect to time. So with related rates, over this entire section, I like to spend today and tomorrow. There's not many sections in this book where I do that. Optimization and related rates, Calc 1. Let's spend 2 days on it. Why? Because every problem changes. You're going to differentiate everything with respect to what? With respect to time. And what letter we can always use for time?
T.
So no more differentiating with respect to x, Amber will be with respect to t. Every time. But then you'll be doing a lot of this stuff right here. Except it won't say dy dx. Maybe it's letter R, you'll write dr dt. Maybe it's letter A, you'll write dA dt. Maybe it's volume V, you'll say dV dt. Do you follow me? You'll continually be doing this throughout the problems. Because you'll be going, I gotta differentiate this. Oh, it's with respect to time. You'll do a power rule and Amber, and then right after you'll write like DRDT or DADT or DBDT or so you'll get used to it. But every time we're finding how fast the related rates. This is rate of change, right? With respect to what? Time. How fast things are changing. Maybe someone's pouring soda into this container here. Maybe someone's draining what? Coffee from a conical, a coffee machine. Maybe someone's pouring water into something. Maybe someone's blowing up a balloon, They're sitting there like, and the balloon's getting bigger and the volume's changing. Area of a rectangle's changing. Let's spend 2 days on this because every geometric figure is going to change, right? Could be area, could be volume, could be a square, could be a circle, could be a sphere, etc. Cool, so let's spend a couple days, make sure we got all this stuff down. So let's start with something simple. Doesn't care if I start with a circle? Will that work? Circle's simple, all right, little circle. What do we want to change? Circumference, how about we change area? We'll talk about how the area of the circle is changing. Cool. Maybe the circle's getting bigger, maybe the circle is getting smaller. In my case, everyone, let's have it such that the area is getting bigger. All right, the area is changing in the circle. Can you give us a real life application? The closest I can do is skin cancer, everyone, but it's not really usually a circle. It usually looks like a blob, especially with me with all the basal cell skin cancer I've had. But what happens, everyone, if you don't have it taken, cut off? You know what it does? It does grow in size. It will. It'll start out like this little, boom, it's usually pink in color, it might bleed, this little thing. A couple months later, everyone will be bigger and bigger and bigger. It'll form up on my shoulder and stuff. I can pull this down, you see like something cut off. And it finally got cut off and it was about this big. It's not a perfect circle, but it's typical like that. So in our case, let's just say this circle is increasing in size, all right? And how fast is it changing? Let's say the radius is increasing. I'll do centimeters. 2 centimeters per month.
2 centimeters per month, okay.
That sound good? Per month? Every month, the radius gets what? How much bigger?
2 centimeters.
2 centimeters. And the area gets bigger. All right. And then my question is, right, how fast is the area of the circle changing? When the radius is equal to 10 centimeters. So we'll start with the circle. By the end of Thursday, everyone, Thursday evening, you and I will probably cover so many different geometrical figures. Right triangles, spheres, rectangles, right? 2-dimensional, 3-dimensional. This one's just 2-dimensional. All right, now if you wanted to draw this, Owen, you could keep drawing what? Circles that kept what? Getting big, all right, now what's going on? Changing it every moment. Every month, that's how much it's increasing. So what do we start out with in every one of these problems?
The
That's
area,
the hard part. You gotta know your geometry figure and formulas. But I think we just know the basics will be good. Everyone know area of a circle?
pi r square.
Let's write it down. We can make a list, everyone feel free to make a list throughout the whole, today and tomorrow, every time you're like, I didn't know that. Area of a circle is pi times r squared. So you start with the formula. I mean, if it was volume of a cone, we would have written volume equals 1/3 pi r squared h. And don't freak out if you're like, gosh, I don't know the volume of a cone. We'll list them. We'll make a list like, what one should I know? Amber, so I know all the geometrical formulas and their volume and area and lengths. The next step, everyone, we're going to differentiate both sides of the equation with respect to what letter?
T.
T. That's what we'll do next. So let's go over here and write dA dt. Cool? What are we going to write? We're going to differentiate all this with respect to what letter?
T.
T. But what's interesting? That's not T. That's a what?
R.
R. So we're gonna do this just like we did implicitly. That's what we're doing. Implicit differentiation. It's almost like you can think of this R with the parentheses. And what do? I do the power rule. Because that's just a constant, right everyone? You don't need product rule, that's pi. Pi is not a variable. So multiply the 2 in front. 2 pi. Decrease this R by what?
1.
1. Or this time I won't put the 1 there. Right? And then chain rule, right next to it, guess what I'm gonna write?
D.
The derivative of R with respect to that letter. Derivative of R with respect to T. DRDT. You go why? It's because of chain rule. Why? We're doing implicit differentiation. Did anyone see that? I differentiated in R. So before with the X and Y, every time it was a Y, we put dy dx. Every time you got some variable that you differentiate, right after it, put d block dt. It was a bit dv dt. All right? Now, how fast is the area of the circle changing when the radius equals 10? So we're solving for that. And that's what that means. d dt is a rate of change. So you're finding the rate of change of the area. So this is what we're solving for. Only thing we gotta do is plug in 2 numbers. We gotta plug in a number right there and a number right there. What goes in for R?
10.
10. And what goes in for DRDT? 2. Now is it 2 positive or negative?
Positive.
Good. Because everyone, if they said decreasing, I would have made that 2 negative. Do you follow me? It's something to remember today, tomorrow, even Monday. Just go, ooh, related rates. If some dimension is decreasing in size, I'm just gonna make the rate negative. That means it's decreasing, the rate is decreasing, okay? You'll get used to it
So
though.
is it like in this case, the R is like the Y,
That's right.
right?
That's right. But get ready for all the letters, but every time treat it like that. And we always do D what? DT.
DT. So like the whatever, the one with the like the third power, second power.
That's
like
right.
the number that goes in, when you're doing the change in.
You got it. And before I write that answer, Amber, you got it. Look at this. And that's just a little square, right? Did you know area of a circle is side squared? Do DADT on this thing. Watch how you can do it. You would say what? DADT. All right. And then differentiate that with respect to T. But that's an S. Well, do your power rule.
So it'd be
2 in
S
front,
over
decrease
DT.
S by what? 1. Then D what letter? DS.
DS over DT.
There you go. You're an expert. You got it. You got related rates down. Why do we spend 2 days? Because every figure is going to change, right? We'll have a couple ships going like this. What shape is that? We'll have to make a picture to figure it out. Good job. Hey, so what's my final answer? Let's put the units. 40 pi
Centimeters
centimeters
per month.
per month. Did I miss anything, or is it centimeters squared?
Centimeters squared.
Brilliant.
Squared,
Now, once
yeah.
you look carefully, you go, what am I finding? What's changing?
Area.
Area. Area is squared centimeters, right? So centimeters squared per month. Right? You go, where does your, well, that had a centimeters per month and that had a centimeters. That's why. And when if you wanted to put your units in here, there was a cm here and there was a cm per month there. That's why it came up like that. Cm times cm, cm squared. Does everyone get that? Yeah. Cool. Did you want to do an area of a square that shrinks? All right. Don't worry, I'm going to give you that worksheet. And the problems I picked from the textbook, I hand-picked them, Kel, so they're all good, and we can work some of those or the next, tomorrow and stuff. Even Monday. So if I don't get every related rates problem that you wanted work from tomorrow, you make me do it Monday.
So our test is.
All right, this is a square, and this time, let's say the side of the square is decreasing (5 centimeters). This time, everyone, per minute. And when how fast is the area of the square changing when the side equals, make up any number you want, Amber. Give us some length. When the side length is what?
4.
What was it?
4.
Wow, if it's 4, then a minute later it won't exist, you agree?
Oh,
Isn't that cool though? You know, I think logically, that's okay. But a minute later, that square would be what? Gone, do you agree? Because if it's decreasing 5 centimeters per minute, a minute after, but that's okay, I'll put it. When the side length is 4, I just thought she was gonna say something like 400. That'll work. But we are making the observation, hey, a minute later, no more square. Okay, what's A equal to? S squared. D80T. What do I do here, Amber?
2s
2S, now D,
s dt.
DS.
over dt.
I put my 2 back here, the S is the 4 that Amber came up with, everyone. How do I write ds dt? How do I write that? Because it's decreasing.
So the 5.
Negative 5. So that means my answer is negative. And when d/dt, my final answer is negative what?
5 times 2 is 10. 40
Centimeters or centimeters squared?
centimeters square per minute.
Per month or minute?
Minute.
Per minute?
Mm-hmm.
But it's negative. What's that indicating? It's indicating that the area of the square is what? Shrinking at that moment. Remember, this is still instantaneous rate of change at that moment. Everyone care about that? All right. The textbook problems, everyone, they're great. But this is one of those sections. Let's do like a few problems together. So I made a worksheet, it's got 3 problems. I think I left you enough space to write on here. If you'd rather write in your notebook, and feel free to write these in your notebook. Let's do 3 of these together. When we're done this sheet, I think you'll see triangles. I also think you'll see cones. You're welcome. And yours, Sarah?
Oh, they don't really do.
She probably told me about that and I forgot.
Yeah, so both of them, yeah.
Can you borrow your notes?
Yeah, recording.
Oh, thank you so much. Oh, awesome. You're recording?
Yeah.
Hi, Sarah.
Anything else you wanna say?
That's about it. Hope you have a good orientation. Very tall, though. Hey, you're welcome. Amber, should I give you a copy of this to give her?
Oh, yeah.
Hey, you're welcome.
You too.
How many copies?
You too, or she wasn't here.
Oh, that's right. I'll say hi, Lincoln. Hi.
And 2. 1, 2. There you go.
2 copies for them. All right, everyone. We're gonna have to make some pictures in this section, right? Pictures tell us the story. So read through that problem. If you have to, reread it, right? I do want to give you a heads up. You get a lot of right triangles. Not every problem, but you get a lot of them. Just because of how things move. Ship moves this way, ship moves that way. Plane's flying this way. I'm standing here and then the plane flies over me. And you see how that distance changes. You don't see a right triangle?
Mm-hmm.
Or a train passes by. I'm standing right here. Here's this looking. The train comes by and goes like that. You're like, okay, how far is that changing? So, planes, trains, automobiles, you bet. You will get a lot of right triangles. I know. Did you see that movie? That's good. That's very fun. He's going the wrong way. Going the wrong way. How does he know it's right?
Is that a Steve Martin?
Yes. Remember when he's going the wrong way? We're going the wrong way. Let's see that. All right, let's look at this first one. A police cruiser approaching a right-angled intersection from the north. All right. Here comes the cruiser. A right angle, I guess that'd be like that, huh? There's the intersection. Okay, here comes the cruiser approaching from the north. So you can make a police car if you want. There's the police. Chasing a speeding car, has already turned the corner, is now moving straight east. So the car's down here. They still chasing those guys in New York?
Oh yeah.
So they haven't caught them?
Nah,
They might be in Canada then, right?
could be, yeah.
If they're in Canada, they're gone.
Did you see them leaving a smiley face for the police?
Yeah, I know.
That was funny.
It's like something out of a movie, like Shawshank Redemption. Escape from Alcatraz. All right, and here's the speeder. I'll just call him Dude. All right. He's going this way. The dude's going this way, right? I got some numbers here. When the cruiser is 0.6 miles north of the intersection, the speeding car is 0.8 miles east to the east. The police determine with radar the distance between them and the car is increasing at 20 miles per hour. Oh, the distance between them is increasing, they said.
Mm-hmm.
I say we draw a line about that. I want the distance. What shape do you see? Right triangle. What's Pythagorean theorem? So you might be using that a lot. 3.8 or 2.9. Yeah, a squared plus b squared equals c squared. And Amber, we're talking about after we do this, eventually we'll get a dAdt, we'll get a dBdt, and we'll get a what? dc to t, right everyone? That's what we'll get when we differentiate. You'll get a little dAdt off to the side once you differentiate in dB. That's what'll happen. If you don't like A, B, and C, you can use all the letters. But in this problem, what has to be length C?
Hypotenuse.
Good. All right, this has to be C. I don't think they give it to me. I don't think they give it to me. I do believe they gave me A and B though. Because they're always asked this question at one instant, okay? And it was at the instant when he was 0.8 miles to the east, and this was 0.6, right?
Mm-hmm.
0.6 mile, 0.8 mile. So is everyone okay if I call this A? That's A, right? And this is?
B.
But they didn't give me C, so do you mind getting it right now?
Plus 1.
What theorem?
Pythagoras, right?
Not through Pythagorean theorem. And you go through the math, some people have already figured it out. It's a perfect one. 1. And when C is 1, look. 0.6 squared plus 0 squared, C squared. C squared equals 1.0. What's the square root of 1.0?
1.
1.0. Wait, what about plus or minus?
You don't need it.
Length can't be negative, it's a length. So how far was this at that instant? 1 mile. Now I'm gonna change color chalk. If you want to color code with me. Can we talk about the rates given in this problem? Because they did give you some rates. What was dCdt? And was it positive or negative? What did they say? The police determined radar that the distance between them and the car is increasing
So it's positive.
at 20 miles per hour. So I'm going to change my color, and I'm going to talk about how dCdt is actually 20 miles per hour positive. This is increasing. Because what's happening a few seconds later? The police is what? There, and then the car is what? There. That distance what? See? So at that moment, the distance was increasing. Cool. Did they give us any other rates? Just one more rate they gave you. Everyone, look at the last sentence.
The cruiser is moving.
If the cruiser, that's the police cruiser, is moving at 72 miles per hour at the instant of measurement, what is the speed of the car?
Speed of the police
Gotta
car?
figure out that speed of this guy. Speed of the dude.
Dude, okay.
The speed of that what they call him, the speeder. So when the cruiser is going, what was it? 72 miles per hour? So Amber, do you know where I'll label like a D something letter DT and put 72 miles per hour? Because it's a rate, it's one of these. They said it was the cruiser, the police cruiser. They said he was going 72 miles per hour.
So DADT.
All right, that's an A. So I'm gonna write, everyone over here, dAdt
72.
equals
72
72, if you want to put the units, miles per what?
hour.
Now, I want you to look at something carefully. Look at this image. Look at this image carefully. Think about it a moment later, this instant. What's going on with this length?
Decreasing.
Is it decreasing?
Uh-huh.
Guess what I have to do here?
Negative.
That's probably the hardest part of this whole section. I need you to look, observe that picture that you got, the sketch. Look at something and say, well, is this side increasing or decreasing? Well, that side's decreasing. The cruiser is heading towards the what? The intersection. The other side's increasing. The answer dBdt is what we're looking for. And the expression we're looking for this problem, what are we trying to find, the unknown? Here it is. What is, oh, I gotta use
dBdt.
yellow. What is dBdt? How fast is that car going? Rate of change of the length B with respect to time. Cool. Why did I make this next? Because what? This whole length in this right triangle, we're gonna call this letter A, and that length of that right triangle is gonna shrink a moment later. It's gonna look like that, right? Cool. So at that instant, it was shrinking. Where do we start? Now, everyone, I need you to differentiate everything with respect to what letter?
A, B.
T. All right. Do power rule. 2 in front. Decrease it by 1. What shall I write right next to it? D-A-D-T. Why? Chain rule. Why? We're doing this implicitly, right?
Mhm.
All right. D-A-D-T. What does this become?
2B dBdt.
2B or not 2B? Yeah.
2C.
And then this one becomes.
2C dCdt.
Hey, if you want to, everyone in this class, if you get a lot of these problems, and you do in this section, look at all the 2's. What could you do if you wanted to make that thing easier to solve?
Factor on.
Yep, divided 2 on both sides. So I'm going to do that. You'll see it come up often. Look, 2, 2. I'll divide 2 on both sides of the equation. Some of you may just start right here on some of them. I mean, yeah, it's okay to just even start here. You might get tired of doing this every time. You may just start right there. Now notice there are 6 things to fill in. I believe we have 5 of the numbers. You should always have 5 of the numbers here. And then the 6th is the unknown. Just be careful with the positive and the negatives. What's that?
0.6.
It's DADT.
72. Negative 72.
Good call. Negative 72. Right?
Because going,
Because that was shrinking. Good. You can imagine on the WebAssign questions I get for online calculus for later rates. They did every. If I love them, they'll attach work, and I go, "What's your question?" I go, I don't know. And I spent 2 hours on this. I'll find out. I'll be like, "It's double by big. That's negative." And everything will work out. What's that?
B is 0.8.
0.8. Oh, we don't know this. Unknown. Unless you want to call it X. Do you like to call this X? You can.
We can leave it dBdt.
Yeah, I'm with them. Leave it DBDT. I'm with Art. Leave it DBDT. But you could make it an X if you're like one of these people. I like to always call for X. What's C?
C is 1.
1. DCDT was what, 20 pounds?
20.
Now, how do you algebraically solve for DBDT?
So you have to take the 0.6 times 72, add them with 20, and then divide by 0.8.
Good call. Whatever that number is right there, it's negative. We'll add it on both sides. Do you want to see what it is real quick? What is that number? 0.6 is 72. 43, so negative 43.2 plus 0.8 times DCDT equals 20. Let's add that on both sides, right?
Uh-huh.
You get 0.8 DCDT equals 53.2. And last step, what do we do?
Divide by 0.8.
Hey, our answer's going to be positive. I hope that makes sense to you. Is that car increasing? I mean, is this length right here increasing in size?
That's 63.
Oh, you're the best.
And it's also dB by dt.
Oh, you're the best. Right here, I want to just say, don't change the letter. In fact, I'm going to keep that yellow. DBD. DBD. And DBD. And what's 63.2 divide 0.8? How fast are they going?
79
They're cruising.
miles per
They're
hour.
flying, everyone.
That's not that fast though.
Yeah, I know, that's rush hour, you're behind everyone in rush hour. 79 miles per hour. What up with that? Great job. Try the second one. ladder 13 feet long, pressed against the vertical wall. All ladder slides away. Make a picture though. Hey, you always start out by drawing a picture. Everyone, it doesn't matter which side of the wall I put the ladder on, true?
Uh-huh.
Is everyone okay if I put the ladder on the right side? I mean, I could have put the ladder here, I'll just put it on this side. There's my ladder. How long is it?
13.
The ladder is 13 feet long?
Mm-hmm.
Okay. What letter can I call it? See, everyone spots the right triangle already. I call that C. They see the right triangle already. That's C, that's 13. Now what else do they see? Bottom ladder slides away from the wall at 2 feet per second. Oh, but I'm gonna draw this picture again, and I apologize. Maybe I shouldn't rush to my picture, because look at the end, they go, how fast is the top of the ladder sliding down from the wall when the bottom of the ladder is how far from the wall?
12 feet.
So maybe I should draw this picture like this, right? There we go. And that's a little bit better image. If this is 12, this was what?
13.
Okay, that's C. I'll call this B. This is A.
5.
Did they have the big yardstick in here? No? No? Boo. All right. Let's pretend that's the ladder, right? I want you, as you're working this problem, to think about how the sides of that right triangle are changing. What sides are shrinking, what sides getting bigger? Can you see it? And that's what's going on here?
Mm-hmm.
You all see that right, as the right triangle changes? Good. Can you get that on there?
Yeah.
There's your ladder, it's like it's sliding, we're talking about what's going on when that's 12 feet here and this is 13 feet long. But we all can tell that side is what? Decreasing. That length of that right triangle is decreasing, this length is increasing, right? Something funny was going on with length C though. Different from the car chase problem. Good job. Outstanding. Oh, and this is different from the other problem in one case. That C value, she says, is always staying constant. It's always 13, right?
Mm-hmm.
It wasn't an adjustable ladder that there was changing throughout the whole problem. It was always 13, 13, 13, 13, so. That's interesting. So, I think I'll start there. And Brett, probably was the hardest part to this problem. Could have thrown us off. They won't tell you DCDT. Do you want to know why? If C's always 13, then how fast is DC, how fast is it changing? It's not changing. So it's always going to be what? 0. Does that make sense?
DCDT would be
That's right.
0.
There you go.
Because it says it rests, yeah.
Right? Because that ladder is always going to be 13 as it slides down. It's constant, never changes. Cool. Now, did they give us any other rates? What was this 2 feet?
2 feet at
Go
the bottom of the
45.
ladder.
All right,
slides
where's
away.
the bottom of the ladder?
The B.
There. So when they said this, there's the bottom of the ladder. So they're talking about this length here. Look, bottom of the ladder. And then they said something about it's going away from the wall at a rate of 2 feet per second. So that's a B. So dBdt positive is 2 feet per second. All right. I've got B. I've got dBdt. I've got C. I've got dCdt. I'm stuck. How do I get that?
5. That's it.
How'd you get that?
13 square minus 12 square.
Pythagorean theorem.
It's a perfect triangle though.
Oh, you got those memorized. Anybody else know these?
I saw this
That's
one
the only one I
too.
know.
I love that. That's smart if you know the common right triangle lines. 3, 4, 5, 6, 8, 10, 5, 12, 13. Anybody know any others?
1, 2, root 3.
What was it?
Is it 1, 2, root 3?
No. Oh, 1, 2, root 3. Yeah, that works. There's a 1, 2, root 3. 1, root 3 too.
Yeah.
I'll go down to anybody know the one that starts with 8? 8, 15, 17, and my favorite, 7, 24, 25. I don't know if you'll see that one too often, but you'll probably see these. It just saves like a minute of work to do Pythagorean theorem, right? Hey, thanks, you saved me a minute. So a lot of you knew that was a 5. I'm gonna put it. Well, what's the unknown in this problem?
DADT.
All right, try it, see if you know the work.
So DADT should be negative, right?
That's right, he goes, your answer should come out negative.
Can I,
Expect it, expect it, expect it. Your answer should come out negative, he's saying. Well, expect it.
can I interject one second? Because what
Sure.
happened is, if you look at it in a Cartesian coordinate, x is increasing, so the DADT has to be increasing, and y is decreasing, so that has to be negative,
That's right.
right?
Yeah.
You can do it that way too.
It's very good, Art, seriously.
Thank you, sir.
It's really good.
So,
All right, here we go.
square,
A squared plus B squared equals C squared. And then 2A DADT. It's like differentiate both sides of the equation.
DADT plus 2b
2B DADT.
DADT.
2C DCDT. What can I do with all those 2's?
So two,
Get them out.
so 2c DCDT, you can say that that's 0.
Right? I love that. Did everyone see what happened over here?
Yeah, so.
Love it. Because that's C0, you're 0.
And that's what.
Now, I do like to take these 2's off, so I think I'll write it like this. Okay. That's 5. That's D82. That's 12. That's 2. Alright, what do we get? Subtract 24 on both sides, divide that.
By 5.
My answer is negative. Was it supposed to be negative?
Yep.
Yeah.
Mm-hmm.
You can leave it like that unless you want to make that a decimal.
4455
But you gotta write units.
Negative 4.18
Is it feet squared or feet?
feet per second.
feet per second.
Feet per second, very good, because we're not talking about area here, we're talking about length. Feet per second.
Because each of the other ones are feet per second, so when you DADT is going to be feet per second.
Yes.
So, Alan, basically all related rates are kind of like a velocity.
Yeah, you're right.
Right.
Actually,
They're all velocities. We're always finding velocity. Every time, he's right. At an instant. So go, flip it over on the back side, let's go 3-dimensional. What is it? All right, there we go. It's a cone.
Conical tank, 9 feet per cube.
Now, water runs into a conical tank. The tank stands pointed down, has a height of 10. Let's draw a picture. Conical tank. All right, pointed downward. Has a height of 10, base diameter of 10. Okay, not drawing a scale I want, but that's 10. This is 10. 10 and 10. How fast is the water level rising when the water level is 6 feet deep? And when they said water's going into this tank, right? How fast?
9 feet cubes per minute.
So if we want, maybe we'll just go like this, we'll put like, here. 9 cubic feet per minute. Here comes the water. I'll draw an arrow, it's going in. So that means volume will increase, right? Sometimes they do the leaking faucet stuff or the leaking cone, so keep that in mind. How fast is the water level rising when the water level is, how deep?
10 says.
At 6
6
feet,
feet,
right?
yeah.
So in that six, that number 6, I don't plug that into the very, very end. Right? Seriously. Once I get it all set up, once I differentiate, and I got a little h in there, because h will be 6, right?
Mhm.
Do you follow me? But at the very, 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 very end, maybe I won't even write it down now. I'll wait till the end. I'm just going to plug in 6 for h. Okay?
Why would you, oh, because 6.
We wait till the end, don't we? Didn't we do that with this code?
Yes.
The same, very similar. We start with the actual formula. When we get it all broken down and neat, then we start substituting numbers. True?
So then H would be 6.
So I'll let h equal 6 once I get the whole formula worked out.
Oh.
Cool? But we gotta start with the formula. And on what is volume of a cone? 1/3 pi r squared h. We'll start there. Now, make a note about cone problems. Look how many variables there are on the right side of the equation.
3.
And just go to the right.
2.
On the right side of the equal sign, everyone, there's an R and a what?
H.
H.
Product.
And he's like, you're hitting on it. You're like, we'd have to protocol, but we're gonna do even better than that. Every time we do a cone problem, with related rates, everyone, we're gonna start the problem with one variable on the right side.
We're gonna
That variable's gonna be height. So we're always gonna start this problem before we even differentiate and get everything in terms of h.
Okay.
You go, why? Because geometrically, there's a nice little relationship going on between the h and the r, because if you've taken geometry before, there's something called similar right triangles. Have you ever heard of that? Triangles that are similar?
Uh-huh.
And so do you see like a triangle in here? Like this thing shrunk to here, and then it's at what, how high? Maybe 6. So you see that, I'm gonna draw 2 triangles here. This is just a geometry concept, but I wanna show you why we can eliminate r at the very beginning.
Okay.
There's a relationship, and there's similar triangles. 2 triangles are similar in all geometry, as long as you've got 2 angles congruent to 2 other angles. Well, do you see this triangle and this triangle?
Uh-huh.
Don't they both share that angle?
Yep.
And have you ever heard this phrase, alternate interior angles are congruent?
Uh-huh.
And then I'll put 3 here, these angles are equal. So what I'm saying is, every time you have this type of design, with the triangle, which is true with the cone, you have similar triangles. And that means, in this case, we could say like, let's say I'll put this triangle out now. Here's the big triangle, this is the what?
Small.
Small triangle. I can say like, this letter, I'll call it D1, I can call this D2. These sides, corresponding sides are in proportion. So if this was like, I'll call this L1, L2, but you know what we could say? D1 over D2 is proportional to
L1 over 8.
L1 over L2. You can do that, it's a rule of geometry, it's a theorem, deals with similar triangles. So I want to point out, you always have similar triangles in there. So to start out with, everyone, let's do this. First of all, I want to write this whole equation in terms of what?
H.
Alright.
So that's 3V over pi r squared.
Oh, I love it. I love it, everyone. So I want to write this whole thing in terms of h. So I need a relationship between r and h. Alright? So, how about I do this? Now when I'm going to solve for r. Let's write this. R is to h. This must always be the proportion in this picture, but I need you to go into that image right there and tell me the radius and the height of the entire cone.
10 over 10.
What's that height right there, Amber? 10, so I'll put that here, and I need to look closely.
Oh, 5.
What is the radius of this
5.
cone? Radius is from the center out. Someone agree?
Uh-huh.
Yeah.
Good,
Did
Josephine.
you get the R over H?
I just wrote it as a proportion.
Why?
Because
Similar to-
of this, what I just explained for 2 minutes. With these 2 similar triangles, we're gonna be able to write this R in terms of H, because this proportion will always hold true. So what I want you to do, Josephine, is always write R over H with the cone problem. Cool. So now, what's his radius?
5.
What? So always do this with the cone, but what I need you to do now is solve for R. Can you do it? Oh, you might reduce this. What's 5 over 10?
Half.
R over H is that a half?
Mm-hmm.
Valerie, can you isolate R?
Yep.
2R equals,
No,
Well,
no.
how would you get that H off that side?
Divide by 8. So
I've
basically,
got R over H equals a half. How can I get R by itself?
half of R.
I can multiply an H on both sides, right?
Yep.
yeah,
What do you get?
So half of I.
H over
2.
2, is that what I got there?
Uh-huh.
So I mean, what is the continual relationship? Always in this cone. Radius will always equal half the what?
Height.
Throughout that whole thing as it fills up. And it's because it's similar triangles. So every time we do a cone problem, and I like your question, Josephine, you and I are gonna go off to the side before we even differentiate. Here's the formula. We're gonna say, well, what's R to H in this entire picture? So even if this was like 30 and this was like 28 or something, find the radius, find the height, set that ratio to this, and then solve for what letter? R. Because now, where can I substitute this? Where's this going? Right there. Before we start the problem, we can write everything in terms of one variable, H, every time with a cone, because of geometry. So you want to do that. And here's the other thing. Remember you said Bell-Raj product rule? Great, but see, we weren't given any radii distances, were we? They didn't tell us how fast the radius was changing. That's why we want to do this. The only thing they told us was how fast that water was coming. So, everyone, what do you get?
So 1/3
1/3 pi. Don't forget there's a squared there,
H over 2 square.
right? H over 2. I think I'll put it in yellow just to emphasize it. Look at this, everyone. Boop. There's R. Well, what was right next to that, huh?
H.
Now, I encourage you, everyone, before we do differentiation, can we simplify all that junk?
Yep.
Make that look a little prettier, Amber. All this junk in here. What do we got? You got H squared, you got a 2 squared in the denominator, and you got an H over here.
So H cube over 4. 1/3
So you got a 1/3 pi
H cube over 4.
H squared over 4 times another H. And then Art just told me H squared times H is H what?
H cube.
Cubed. Everyone, what's a 4 times a 3 in the denominator?
12.
Pi over 12 H cubed. Oh, that's so pretty now. Oh, there we go. That's where we're starting. I haven't done any differentiation yet, right? But let me rewrite this whole thing. Here we go again. What's volume equal to? Pi over 12 times
H cube.
And the beauty of this, Josephine, we've got one variable. We're saying volume is in terms of one variable. It's not an R and H number. And you can do that every time with every cone. If the cone is tilted this way or if it's like this. Because one of the problems in the book, they got like sand, a pile going like this. It's building up, they're pouring sand, and it's like one of these conical piles that just keep building like this. You do the R over H. And then solve for R, so you get it all in terms of A. And you go, Evan, why don't we do the opposite? Solve for H and then put it in terms of R? Because Evan, in real life, it's really difficult for something to go inside, like, let's say this is water, some kind of fluid that could harm me. It's tough to get in there and say, oh, how far is it from there to there? I'm on the outside of this thing, I don't know how far it is that way. This is easy to measure. It's easy to me, just get out a ladder and get up, this is the height. So he's talking height. All right, let's do it right now, everyone. Ready to differentiate? All right, D, what's that letter?
V over dt.
All right, that would be rate of change of volume with respect to time?
Mhm.
True?
Yep.
You ready to do power rule with the chain rule? You know afterwards I'm gonna put a DH what?
dt.
DHCT, but help me do power rule. 3 in front.
So 3h square.
Some might go, wait, do we need product rule? No, that's a constant. 3 times pi over 12. Decrease this by what? H squared. And then write
dh dt.
dH dt. Implicit differentiation, chain rule. Hey, can we reduce 3 12ths?
Yep, 1/4.
So I'm gonna write it again, just because we're gonna do stuff three times. dV dt is pi h squared over 12 dH dt. Oh, thank you. Now, where do I put the 9? I think the units give it away. You know, there's two things. Is the 9 here? I'll be great in tests. People just throw down a 9 here, or they throw down a 9. Where's the 9?
DHDT.
DVDT.
And 6 goes.
How do you know what's DVDT is the 9?
It's feet cubed.
Feet cube per.
I love it. You're looking at, I'm gonna use these tactics, these ideas. His suggestion is because it was feet cubed. Look, cubic feet. That's changing what?
Volume.
Volume. So if you're concerned like, well, I don't know which one to put, look at the units, it'll give it away, right? That's 9 cubic feet, that has to be that. If you're confused, like, I don't know which one it is.
But how do you know it goes down there?
You know it's here, Amber, because of this thing, right?
Cubic, yeah.
Cubic
Yeah,
feet,
velocity.
you're like, that's changing volume, DVDT. Now, before I screw up, help me out, is it positive 9 or negative 9? It depends. Is the water going in the cone or out of the cone?
And so it's
In the cone,
positive.
so it's positive, good. Good, volume's increasing, good. And finally, at the very end, everyone, I recall 5 minutes ago, I said something about the last sentence said, do this when the height of the cone was how high?
6.
6. When the level of the water was 6. So put a 6 in for H. And we can solve for DHDT. All right, 9 equals pi times 36 over 4.
Isn't it gonna be 6 squared?
What's 36 over 4?
9.
So 9 equals 9 pi.
You can cancel 9 out.
Divide up 9 on both sides?
Mm-hmm.
Amber, okay? Yeah?
Yeah.
What, divide 9 both sides?
Yeah, divide 9
Nice. Last step, divide the what?
By pi.
Just leave your answer like that. Just leave it like that, unless you want decimal. That's exact. Now, what's on units? I have to put units. I have to put units.
Feet per.
Feet, cubic feet.
Feet per minute.
Feet per minute.
Galrash, excellent. He goes feet per minute. That was change in height. That's the length, right?
Mm-hmm.
Before you think, wait, do I do cubic here? How fast was the height changing? When it was 6 feet high, the water level. DHDC, feet per, it was minute, right? Yep. 1 over pi, feet per minute. Yeah? So I love all your questions. Josephine, I loved yours. She's like, what are you doing with this R rate? We'll always do that when it's a what? Cone. It's not like there's a bunch of cones, but everyone, would you look at number, we won't do it now, but you might say, hey, can you do it tomorrow? Look on page, where is it? Top of page 249, what do you see? What image? See it?
Corner, okay, yep. Number 27.
But I'd like to do one more related rate. Let's find a good one, okay?
Can we do another one like that?
Oh, I think tomorrow, I bet you we'll do another cone problem. I'm telling you, the one that had it, there's a gravel pit. Number 27, see this?
What page?
You don't have to do it now, but you definitely
249.
try, if you want to try it tonight, Amber, we can do it tomorrow. It's in the related rates, it's on page 249, do you see it? The top of page 249, can you see an image from here? They get this gravel and they're pouring it down, it's forming that cone. And before you even get the problem in, doing differentiation, you're gonna what? You're gonna average.
You have to do it for every cone problem.
That's right.
Average, okay.
Because they don't give you information on the radius and stuff. I guess you can H over R, but still just solve for the letter what, R? Cool. All right. For, Amber, do you want to hear the first few words of number 23? Water is leaking out of an inverted conical tank. All right. Hey, we already did 2 right triangles. I think we had enough of the right triangles for the day, Joe?
Mhm.
Do you agree? But let's definitely do another right triangle tomorrow. Because before you think, I've got right triangles down, sometimes the problems in the book, let me read it to you. Listen to this problem. Make me do this tomorrow. There you go. At noon, ship A is 150 kilometers west of ship B. Ship A is sailing east at 35 kilometers per hour. Ship B is sailing north at 25 kilometers per hour. Then they go, how fast is this between the ships changing at 4 p.m.? We've done enough right triangles today, but let's do a problem like that tomorrow, because do you notice they said what's going on at 4 p.m.?
Uh-huh.
So we gotta think about how big that triangle got after 4 hours, true? We gotta make a really good picture. And it all depends where these ships were at the beginning. Cool? So we'll do 14 tomorrow, but I think for the last problem, and let's do something we haven't done. We've done circle, we've done square, we did 2 right triangles, now we did what? Cone?
Cone.
So I'm just scanning over here, and I notice number 12 looks good. It's just something different. And everyone, after I do this problem, would you remind me, because we'll be able to get out, if anybody's like because our test isn't until what?
Tuesday.
Tuesday. So we'll be able to wrap up related rates tomorrow, do a couple more of these problems. So Monday's basically going to be mostly what? Just review, questions from everyone. If you're like, yeah, but I've done every textbook problem. I've done your entire chain rule worksheet, right? And you want more, I've made more practice problems, all right? So that's why I'll make sure that anybody in here, and Sarai asked me about these, so I'll make sure to give her a copy of this as well. And there's a bunch in here. And of course, you're probably gonna want the answers, so I'll put the answers in Canvas, everyone looks at that. I won't print those out, but if everyone wants to work those, you can put them in Canvas. So this is number 12, Aaron. They call it a snowball. All right, so that's what? That's sphere, do y'all agree?
Mhm.
All right, a snowball melts but then they say its surface area decreases at a rate of 1 centimeter squared per minute. All right, so and here we go. Snowball melts. So what is happening to the surface area and the body?
Decreasing.
Decreasing, good. And you want to draw a sphere, you can here. It's melting. And what they said was, surface area decreases, how fast? At a rate of 1
Centimeters square per minute.
centimeter squared per minute. All right, last problem. What's their question now? What are they asking? Find the rate at which the diameter decreases when the diameter is 10 centimeters. So what are we looking for? How fast the
Diameter is decreasing.
diameter decreases?
So the initial diameter is 10 centimeter, right?
That's right. I'm gonna go off to the side here, before I forget. Is diameter equal to 2r or is r equal to 2d?
R equals to
D equals what?
D equals to R over 2R.
Is that right?
Mhm.
And before I forget, because you know as well as I do, most of these formulas are written in terms of radius, aren't they?
Mhm.
Give me the area of a circle again. Pi
Pi R square.
r squared. Oh, it's written in terms of r, isn't it? Anybody know the circumference of a circle?
2 pi R. Or
2 pi r.
Or pi D.
Now a lot of you say pi d, but a lot of times everything's written in r's. This problem talked about how fast the what? Diameter is changing, so before I get started, I'm just going to put that off to the side to note, oh yeah, diameter is twice radius. Okay? Now, how fast diameter changing decreases? Find a rate at which the diameter decreases when the diameter is 10 centimeters. Okay. The only way I can work this problem is if I know the surface area of a sphere formula, right? So if you're like, well, I don't know it, don't worry.
4
I'll
pi
put it
R
down
square.
right now. Here we go. First of all, I want you to know volume. So this is volume of a sphere. We didn't need it for this problem, but I thought it's good to know. That is volume of a sphere. 4/3 pi r cubed. Oh, please feel free to ask me right for a test if you're like, I have trouble remembering the volume of a sphere formula. You know, just meaning you go, is volume of a sphere gonna be out? Yeah, I'll give you a heads up. Cool. Yeah. Now, you know what's cool? The surface area formula.
4 pi r square,
If
right?
you don't wanna memorize another formula, did you know if you just differentiate that with respect to r, you'll figure out the surface area of a sphere formula? So let's do it. Makes it an easy way to remember surface area of a sphere, right? Just differentiate that, and you'll know the surface area of a sphere. Try it. Let's have you go.
Right there.
3 times 4/3.
So that's 4.
There it is. So that's where I'm starting my problem, everyone. S equals 4 pi r squared. Isn't that cool? Do you know this works with the circle too? Watch. What's the area of a circle?
Pi r square.
Would you all differentiate that with respect to r? You'll get circumference.
Yeah.
Isn't that cool? Isn't that neat? I know. The only thing is now you gotta figure out what other geometric figures this works on. Works on volume for surface area. All right, now we're gonna differentiate this with respect to time, right? All right? You go, hold up. This is what I was thinking, everyone. We can do it and stuff, but didn't they say something about how fast the what? My goodness, why did they ask about diameter? You and I, before we start, can we put this in terms of data? So it'd be just like that volume of a cone thing, because they asked about diameter, before we start, what can I substitute here? Now be careful, is it 2D or D over 2?
D over 2.
Yeah, look here. What would R equal? There you go. So I'm gonna take this. Because the question said mention diameter, let's put that at the beginning. 4 pi d over 2 squared gives me, ooh, I like it. Maybe that's an easier way to remember. What is
Pi
it?
d square.
Ooh, I like that. I didn't know that. I should know that. Pi d squared, that's an easier way to remember that formula. I want the surface area of a sphere. Surface area of a basketball. Pi d squared. It's just pi d squared. All right. Now we're going to differentiate that with ds dt.
ds dt equals to 2 pi d
2 by d.
over dt.
And what do I write right next to it?
dd over dt.
Oh, this is going to look funny, huh? d dt. Everyone, if you want to make this like a delta, like that, for diameter. So I'll write d dt. So it doesn't bug you? That work?
Then why is it DS?
It's the
Oh.
surface.
Differentiate that with respect to time, differentiate this with respect to time. Right? Didn't we always do that? Didn't we do it with the area of a circle?
Yeah.
Didn't we do it with the cone? We did dVdt. We do it with the triangle every time. We d8 everything with respect to t. So we got to hit both sides of that equation every time with respect to a t every time. Now, where's this 1 go?
Surface area is decreasing, right? So that's it, yeah.
And is it positive or negative?
Negative.
Man, you're good. Everyone agree?
Uh-huh.
Look, Nick. Deep. Increase. 2 pi. I don't know this thing, but
We know the
what was
diameter.
this number they said?
10.
Remember they said when it was 10?
Uh-huh.
Put a 10 there. What's the answer? Negative 1 over 25. What were the units? Centimeters per minute? Does that one agree? Just extra practice. These are extra practice. Great question. I love it. Before I keep passing these out. She goes, I thought this was centimeters squared per minute. Josephine, think about what you and I were solving for. They gave us this, which was centimeters squared. The question said about this snowball, they said, find the rate at which the diameter decreases. A diameter, right, is not three-dimensional. A diameter, right, it's just this 1 unit length. So we're not doing unit squared or unit cubed. Just going to be centimeters. So a lot of times you gotta think about it when you're very at the end, you go, wait, what are the units here? She wanted to know this one problem, that's serrated, and tell her one I thought she'd have fun with, the problem, tell her it was that one. Yeah. Yeah, tell her that one. There you go. Everyone, tomorrow we'll continue with related rates. Once we wrap that up, and I love that problem. Thanks for bringing that up. See any others like that, let me know. Hey, what are we gonna do Monday?
Review.
Second, say anything you want, anything. It could be these, it could be textbooks, right? It's all right, thank you.
Ellipse? You're asking for ellipse? That's for ellipse?
Yeah, 'cause I thought the DD would look weird. So I just wanted to change it to something. Yeah, do you mind writing DDDT? Oh, she doesn't write. I was thinking about, maybe I should have just capitalized.
No, he wrote down the answer.
Yeah, maybe I should just done like D, big D. You okay with all this? Wait.
Because I thought it was a 5.
Let me pass these out, I'll help you. There you go. There you go. Some extra corrections.
Actually, I think I do.
Some extra corrections. You can read it. I put the answers in Canvas. All right. I gotta help her. Right?
You were asking?
You're asking for ellipse?
No, it just depends.
Yeah, but they need some diameter.
Oh,
Oh,
They give it the other. I promise. It's in the front. At the very end of the question, they go, blah, 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 blah.
all right, buddy, take it easy.
Yeah. That's it. That's exactly right.
All right, Courtney, see ya.
Yeah, but they make it all sound confusing. And when in doubt, just think of derivative. If they said, look at the word, instantaneous rate of change, that means derivative.
No, 3.2.
no, you
Don't,
skipped it.
don't think though,
Yeah.
like I didn't want you to get hooked on this, this is the danger of this thing. Don't let this stress you out, like, oh, this one's on the test kind of thing. It's just, it's more about, get the brain going, and it can't hurt you, it can only help. Look, we did related rates today?
Yeah.
I wish I find one, watch. Look at this. A railroad track, we'll have to do this one more. A railroad track hits cross right angles, reverse down, stand.
See you later.
Blah, 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 how fast, blah, blah, blah. So it's a right triangle problem. Because you have to get the train going like this, related rates. Don't let it